In this video, we are going to go over section 4.4, curve sketching techniques. So in this section, we finally have enough information to graph function using the final version of the graphing strategy. So if you look at a section 4.2 version, this was the first draft right over here. The graphing strategy first draft, we have function about the first derivative and second derivative. Now take a look at our final version. It looks very similar. So all these parts are coming from 4.2, but we add one more step, which is analyzing the original function, but by first finding domain, intercept, and then asymptote. So these are more like an algebra concept, so it's a review. We know how to find the domain, intercept, and asymptote. This is our material this week. So step 2 is section 4.2. 4.1, and then step 3 about the second derivative is section 4.2. Now let's quickly review. To find the domain, how do we find the domain? So domain is where the function is defined, right? So these are the x value where function is defined. Okay. And then intercept, there are two intercept. To find x-intercept in algebra, what do? We set y equal to 0 and solve for x. To find the y-intercept, we do opposite. We set x equals 0 and solve for y. Okay. Asymptote. We have two asymptote, vertical asymptote, horizontal asymptote. I'll put it right over here. To find the vertical asymptote, this is where function is undefined, so opposite of a domain. So this is where the function is undefined. So in other words, in fraction, this is where the denominator equal to 0, right? Because that's where the function is undefined. Where denominator equals to 0. How do you find the horizontal asymptote? Horizontal asymptote, back in chapter 2, this is where the taking the limit of the function as it goes to infinity, that value. So we apply limit as x goes to infinity, f of x, and that value is where the horizontal asymptote exists. And then we'll do step 2, which is a review section to find, partition the number, find where f is increasing, decreasing, and then find the local extrema. Step 3 is section 4.2. We use the second derivative to find the concavity, whether it's concave up, concave down, and then use inflection point. And with that, we have enough information to sketch the graph. So I have two exercises to completely go through step 1, 2, 3, 4. And then I have third example. I picked out that example from the My Math Lab homework problem. Okay, so this is not going to be a single step problem. It's probably gonna take like more than a page because it's a 4 steps with a lot of work. So make sure you are showing the full work when you are working on quizzes and exams. Okay, so let's begin with number 1. In problem 1 through 3, summarize pertinent information obtained by applying the graphing strategy and sketch the graph. So let's begin with the step 1. Step 1 is analyze f of x. So that means I need to find part A domain. So this is a fraction. So we do have function where it's defined and where function is undefined. So domain is all real except when the denominator equals 0. So that's going to be, so the domain is all real number except when the denominator equal to 0, which is x equal negative 4. So in interval notation, it will be domain will be negative infinity to negative 4, not included union with negative 4 to infinity. And this will be eventually used to find the vertical asymptote, because vertical asymptote is where function is undefined. But we will talk about that in a sec. Part B, intercept. Let's find with the x-intercept first. So x-intercept is, to find the x-intercept, we are going to let y equal to 0 and solve for x. So that is 0 equal to x minus 4, x plus 4 to, and then the fraction is only 0 when the numerator equals 0. That means x minus 4 equal to 0. So x equal 4. That's where the intercept occurs. And then you can write the x-intercept also in an order pair. That's 4, 0. Okay. Y-intercept is when the x equal to 0. I'm also going to start highlighting all the so domain, we found the x-intercept. So we let x equal 0, so that's a 0 minus 4, 0 plus 4. So this is equal to negative 4 over positive 4, negative 1. So therefore, we do have a y-intercept. It occurs at 0, comma, negative 1. The y value is negative 1. Okay. So keep in mind, part C, find the asymptote. Vertical asymptote where function is undefined, and then horizontal limit as x approaches to infinity. So let's use next page. Part C. Let's find vertical asymptote first. So vertical asymptote is where the denominator equals 0. That's where the function is undefined. So our function was x minus 4, x plus 4, which means vertical asymptote at x equal negative 4. Okay. And then horizontal asymptote is limit as x approaches to infinity of our function x minus 4, x plus 4. Now, we have learned limit at infinity in chapter 2, so I'm just going to use a shortcut. This is a same degree, so we take the coefficient, right, leading coefficient, which is 1 over 1. So it's going to be y equal to 1. That will be the horizontal asymptote. It's a horizontal line, so that's why it's y equal 1. So I'm also going to highlight these two. So we have both asymptote. Step 1, done. We analyzed f of x. Step 2 is analyzing the first derivative. Step 3 is analyzing the second derivative. Okay. So let's analyze the first derivative and then use it to partition the number and then find increasing, decreasing, and then local extrema. So step 2 is dealing with the first derivative. So our original function right over here. So this will be my quotient rule. I have to apply quotient rule to find the first derivative. So that will be low d high, low derivative of x minus 4 will be just 1 minus high the low. Same thing. Derivative is just 1 all over denominator square. So f prime of x will be x plus 4. If I distribute this one, minus x plus 4 over x plus 4 square. So my first derivative will be x cancel out 8 over x plus 4 square. Now, let's find the possible critical value so that we can partition the number. So this is again reviewing, we have done it many times. Two possible way, either 0 or f prime does not exist. This time we have to do both because it's a fraction. So fraction is 0 when numerator equals 0, but numerator we are never gonna have 0 because it's always 8. So I'm not going to have any critical value coming from the first situation. Second situation, the fraction is not defined on the bottom. So you have x plus 4 square equal to 0. So I have to square root to get rid of square. So that will be x plus 4 equals 0. Subtract 4, x minus 4 will be the number that we will use to partition the number line. So let's do that. If I partition the number, I'm going to have negative 4 here, f prime. So I have two regions. So let's pick a number for a test region 1. So test number, anything that works before x equal negative 4. So I'm gonna say negative 5. And then the second region, the test number that I'm gonna use will be, let's say negative 3, okay? Anything bigger than negative 4, right? So we plug it into the first derivative, which is right over here. So 8 over negative 5 plus 4 square, that will be 8 over negative 1 square, which is positive 8. So that means it's increasing. Okay. And then if I plug it in negative 3, 8 over negative 3 plus 4 square, 8 over 1 square, which is again positive 8. So I have a positive. Increasing, increasing. So what does that mean? We have a increasing on the interval negative infinity to negative 4 and negative 4 to infinity. And then no critical value. This is not a critical value because we have no sign change. So let's write that out. The function is increasing negative infinity, negative 4, and then negative 4 to 0, and then no local extrema. Okay. All right, so that's step 2. Okay. Now let's do step 3 and then talk about concavity and also inflection point. So I need another page. Step 3. F double prime. Now F single prime, I'm going to copy down this one so that I can take the derivative pretty fast. Okay. First derivative was 8 all over x plus 4 whole thing square. So same thing, using the quotient rule, I have low, the high, derivative of 8 is a 0, minus high, which will be 8 times high the low, so that will be, this requires a chain rule, so 2 times x plus 4 all over low square. So square of square, I have x plus 4 to the 4th power. So let's do some rearrangement. This part is a 0 because I multiply 0. Numerator, I'm going to have negative 16 x plus 4 all over x plus 4 to the 4th power. We can cancel one of them here. So my final answer will be f double prime will be negative 16 all over x plus 4 cube. Okay. So same thing, let's set it, let's find the critical value, inflection point. So that will be f double prime equal to 0 or f double prime x does not exist. So I'm never gonna have a numerator equal to 0 because I have 16 constant term. So I'm not having any x value coming from 0. We do have a place where it's undefined, which is the bottom one. So that will be x plus 4 whole thing cube equal to 0. Cube rooted x plus 4 equals 0. Subtract 4, x equal negative 4. So let's partition this one. This time we are using the double derivative. Okay. So we have region 1 and region 2 to consider. I'll use the same test number. So because it's the same partitioning number. So let's just copy this one. But we have to plug it into the second derivative, right? Okay. Okay. So plug it into the second derivative, which is right over here. So f double prime negative 5, negative 16 over negative 5 plus 4 cube. That's negative 16 over negative 1 cube, which is negative 16 over negative 1. I have positive 16, positive. If I take the double prime, negative 3, then I have negative 16 over x. X is negative 3. So negative 3 plus 4 cube. So that will be negative 16 over positive 1 cube. This time I have a negative. So positive means you have concave up, and then negative means concave down. We do have a sign switch, so this is my inflection point. So let's write inflection point. However, what's our domain? Let's not forget about our domain. So this is why it's important. Domain is everything except x equal negative 4. So even though this is this has a sign change, because it's out of our domain, we will not have this one as an inflection point. Okay, so that's one thing you have to be careful. If it's not in domain, even though there's a sign change, we do not have inflection point. So let's write a comment. So here, concave up, where negative infinity to negative 4, and concave down, we have -4 to infinity, and then no inflection point because x equal -4 is undefined. Okay. Now, let's use all this. Step 4 is using all this information to sketch graph. You see that how many pages I take showing all the steps. Step 4 is sketch f of x. So I'm gonna go back and then basically copy down all the highlighted things because those are all my information to use it to sketch the graph. So we have a domain, we have x-intercept. So let's also copy this down. And then we have y-intercept. We also have vertical and horizontal asymptote. And we also have increasing region. And then we have concavity. Okay. Now let me make a grid and then use it. So I have two defined points here. 4, 0 and 0, 1. Let's indicate that. 1, 2, 3, 4. And then 0 point 1, 2, 3, 4. And then we have 0, -1. Okay. And then we have at -4, 1, 2, 3, 4, we have a vertical asymptote. So that means the function will not touch this one. And then we have a horizontal asymptote right over here. Now here, this is how you sketch this one. So there's no points going through this one, so we got the domain. Function is increasing on this region here, -4, infinity to -4, so right over here. Increasing, and then also increasing. So we have an increasing. So let's do this one over here, just like we did it in last lecture video. So -infinity to -4, we have increasing and then concave up. And then from -4 to infinity, we have again increasing but concave down. So concave up and then increasing will be this portion here. You have increasing and concave down, so that will be this part over here. Okay. So, since we cannot think about this, if I put this portion over here, there's no way it's possible because that means if the function kind of have this pattern, I have to kind of go through this one, and it's impossible because there's a boundary. So the only way this part 2 exists is somewhere here because we have a boundary. This is the only free region I can go keep infinity, 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 increasing part. And then we have this portion right over here, and that kind of looks like I can do that. So this will be extending through this one, going towards the horizontal vertical asymptote, and then going through this horizontal asymptote and vertical asymptote. So this will be my final graph right there. And you can kind of you can see that by checking the answer by using the graphing calculator. So let's check. Let's actually type in this whole thing to check and see if our graph looks very similar. So I have x minus 4 and then x plus 4. I should have very similar thing happening here. Yes. So we do have, let me change the standard window. There you go. And this looks pretty accurate on the paper here. Right here. So that looks good right there. So it looks pretty similar. Check, check. Okay, now let's move on to the next example.